Hope you're having a great afternoon. We're going to be working on lesson 1-6. And I wanted to share a little bit about the prep skills that are needed for this lesson. So some prep skills that would be good for this lesson are understanding powers of 10. Powers of 10 means that you're multiplying multiple tens together. And if you multiply 7 of these tens together, you get 10 to the 7th. Now, if you take 1 and divide by 4 tens, you get a 0.0001. So the positive 7 means you're moving 7 to the right. A negative 4 means you're moving 4 to the left. We're going to dive into this more today. Also, repeated multiplication as our exponent here. Multiplying exponents. So if you're multiplying like bases, 12 is our base, then you can add the exponents together. And if you're dividing like bases, so 7 and 7 are a base, you can subtract the exponents. So 8 minus 2. It's not the biggest minus the smallest, it's the top minus the bottom. But for the most part, Desmos is going to do that for us. And like I mentioned before, there are some problems on the back on page 90. Those answers can be found at the end of the lesson. So today we're talking about debt bad, chocolate good. We're not really going to dive into the chocolate, but we are going to dive into the debt. So it says worrying is like paying on a debt that may never come due. But according to an article posted to the website debt.org in 2018, the average household in the US has a little over 103,000 in debt. That's the average house. That means there's some that are way higher and then some that are way lower. And that was 2018. This is the amount of money that they need to pay back at some point. That's not a good thing. And it sounds like an awful lot until you realize that as write this, the federal government's total debt is, get this. Oh my gosh, that's hundreds, thousands, millions, billions, trillions, $22.6 trillion. If I were a betting man, which I'm not, on account of being too cheap to be risk losing money, I'd be willing to bet that over 3/4 of the population can't even pronounce that number, let alone comprehend how ridiculously large it is. For the record, it's 22,617,777,716,240. So if you decide to pitch in and help out, send $10 to the government to help defray some of the debt, your contribution would now be this. That's what your percentage would be. Okay. So in certain fields like governmental finance and the sciences, it's common to work with incredibly large or incredibly small numbers. Using regular decimal notation, this can be pretty cumbersome. So it says, do this and this look very different to you. One is 100 times as big as the other. So in this lesson, we'll use federal debt. We're not going to do the melted chocolate study, but we're going to use federal debt. Okay. So let's dive in. It says, if you check the national debt over the last 90 years or so, you see that its growth, while alarming, follows a fairly consistent pattern. On average, the debt has grown by about 7.9% per year. If that trend continues by 2050, it will be this number. And by 2100, it would be this number. Wow, compared to that number. If you're like most people, including me, so don't feel bad, you have no idea what those numbers actually mean. They're just too big to get any perspective on them other than, wow, those are really big. To make it easier to understand and work with numbers of ludicrous size, we'll use a clever method for writing them using exponents. Okay, and it's all based on the power of 10. So consider the number 300, which we can also write as 3 times 10 to the second. And that means 3 times 100. So this 3 times 10 to the second is the same as 3 times 10 times 10. There's 2 powers of 10. Okay, so here are some other powers of 10 that we're going to work with. Hopefully you start to see the pattern here. So it says, now let's take a look at some debt numbers. In 1930, the national debt was about $16 billion. By 1985, it had grown to about 1.823 trillion. Whatever, right? Both are huge numbers, but let's look at them in scientific notation. So 1930 is 1.6 times 10 to the 10. 1985 is 1.823 times 10 to the 12. So it's 100 times bigger. It's 10 to the 2 bigger, 100 times bigger. Okay, because the first part of a number in proper scientific notation is always a number between 0 and 10. So it has to be a 1 to 9. Okay, to the left of the decimal here, notice that. You can easily compare the sizes of numbers by looking at the size of the exponent. The second exponent is 2 bigger than the first. That tells us that the second det has 2 more digits to the left of the decimal point, which I said is 100 times. So let's look at an example here. It says Earth is about 2.57 times 10 to the 7 miles from Venus and about 4.67 times 10 to the 9th miles from Pluto. About how many times further away is Pluto? Careful, there's more to think about than the size of the exponent. So this is approximately 2.67 that, or 2.57, and that is 4.67. So we're going to divide the numbers. I'm going to share my screen so we can look at Desmos here. Okay. So we're going to take the 4.67 and divide by the 2.57. And so that is already 2, like 1.8 times bigger. So that's 1.8. And the exponents are 10 to the 9th and 10 to the 7th. So that's going to be times 10 squared bigger. So we could actually write this out in parentheses. We could say 4.67 times 10 to the 9 and divide that by 2.57 times 10 to the 7 and see that that is 1.8 times 10 squared, or 181, about 182 times bigger, very large. Okay, so I'm gonna go back to my paper here. So it says the number of people in the US in September 2019 was this: 329,697,000. Write each number in scientific notation. So our unset decimal, we don't show it here, but it's always to the right of a whole number. If you don't see it, it's always to the very far right. We're going to pick it up and we're going to place it so it's just one single digit between 1 and 9 to the left of the decimal. So we're going to pick it up and write it as 3.29697,000. Okay, and when we did that, our number looks much smaller than what it did. So we have to account for those powers of 10. Every place value that we move the decimal to the left, we're moving it a power of 10. So we moved it 1, 2, 3, 4, 5, 6, 7, 8. So that's a positive 8. It says the distance in miles from Earth to the moon is 238,900. And you can see the example up here on how to do this. So again, we're going to pick up our decimal that's right here, and we're going to place it so there's a single digit to the left, 2.38900. And this is times 10. And we move that decimal 1, 2, 3, 4, 5 places. Now, on page 93, we're kind of being introduced to a different type of exponent. These are not positive exponents, but negative exponents. Okay, so 10 to the negative 1 means we're taking 1 and we're dividing by 10. So whenever we have a negative exponent, it means that the power of 10 is in the denominator instead of the numerator. Okay, these are all values that are less than 1. They're not necessarily less than 0, but they're less than 1. They're getting very, very, very close to 0. And here's an example to do that. Moving the decimal point to the right so that there is just one non-zero digit before it. Drop all the zeros that come before the digit, okay, and multiply the result by 10 to some power. And that power is going to be a negative. So when we move a decimal to the right, we're actually going to make the exponent a negative. So it says a typical flu virus measures between this size and this size in meters in length. Okay, so we want to write both of these in scientific notation. So I'm going to pick up my decimal and I'm going to move it so that I have a single non-zero digit between 1 and 9 to the left. So I'm going to put it right there. So it's going to say 8.0 times 10. And I have to mark how many places did I move it. So I moved it 1, 2, 3 for the first period, 4, 5, 6 for the second period, 7, 8. And so it's a -8. And then this one, I'm going to pick it up and I'm going to move it. So I have a single digit to the left. So that's going to be the 1.2. And I have to count how many places I moved that. So there's 3 for the first period, 3 more makes 6, just 7. So a -7. E. coli is a common bacterium that can cause intestinal issues. A typical specimen is about 0.000007 meters long. So again, I'm going to pick up my decimal. I'm going to move it so I have a single digit to the left of the decimal. And I'm marking this 0 here just so I can see where my decimal is. And I moved my decimal 3, 4, 5, 6. So it's a -6. Based on the size of exponent in scientific notation, which is bigger, a small flu virus or a typical E. coli sample? So here's our smaller typical flu virus, and here's our E. coli. And 8 divided by 7 is close to 1. So we're just going to look at the exponent difference. So we have a difference of 2, right? Because if we take a -8 and we subtract a -6, we get a -2. So this is 100 times smaller. Okay, and it's a -2, so it's 0.01, but it's 100 times smaller. So it says, now that we're good at converting from decimal to scientific notation, it would seem appropriate, if not expected, to work on the reverse, converting back from scientific to decimal notation. So that's just what we'll do. So write each number in decimal notation. The number of red blood cells per microliter of blood in an average healthy man is 5.4 times 10 to the 6. So because our exponent is positive, we're going to move our decimal to the right. So there's 1, and now I have to add zeros for my other place values. 2, 3, 4, 5, 6. So 5, 4, 1, 2, 3, 4, 5 zeros. So 5,400,000. That should be right there. Red blood cells. The mass of an average human ovum is 3.6 times 10 to the -9. So because it's negative, I have to move my decimal to the left. So this is going to be 1 time around the 3, and then I need to add 8 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 3, 6. So it says, now let's see if you really understand scientific notation. When a number written in scientific notation has a positive exponent on 10, what can we say for sure about the number? If it's a positive exponent, we can say for sure it's bigger than 1. It's bigger than 10 even if it's multiplied by 10. If a number between 0 and 1 is written in scientific notation, what can we say about the exponent on 10? So if it's written between 0 and 1, the exponent on 10 will be negative. Fill in the blanks. If a number in scientific notation has a negative exponent on 10, to convert to decimal form, move the decimal place to the left because the number is smaller than 1. Okay, we are going to see some printouts now of what it looks like on a calculator. Because if you're using a calculator, sometimes you're going to get numbers that come out and they have this E that tells you that it's in scientific notation. So an E represents times 10 to the something. So this right here would be times 10 to the fourth. Okay. So example 11 says, write the result of the calculation on the calculator screen in scientific and decimal notation. So right here in scientific is 7.44 times 10 to the positive 3. So my decimal notation is 7.44. I'm going to move it 3 spaces. So it's 7,440. So here is a table of different values and what their corresponding power is. 100,000, million, billion, trillion. And then we have 2, 3, 6, 9, and 12. So number 12 says, the size of the national debt in dollars for selected years from 1930 to 2019 is shown in the table in the graph. In the third column of the table, write how the debt would be read aloud. Okay, so if this were 1.6, so if they give us billions, then we know that the exponent here is going to be 9. Right? And this is 908 billion. So this is, oh, I see. That's plus 10. So that's going to be 10 to the right. So that's the billions. So anything between 9, 10, and 11 are all going to be in the billions. So this is going to be 51 billion. This will be 25.7 billion. This is going to be 28.6 billion because we're not yet to 12. This is going to be 37.1 billion. Oh, you know what? Sorry, this should be over one more decimal. This should be 257 billion, 286 billion, 371 billion, my mistake. And then 908 billion, and then we go up to trillions. So this is 3 trillion, 233 billion. And then 5 trillion, 674 billion. And then this is even larger. This is 13 trillion, 562 billion. And this is 22 trillion and 618 billion. And you can see these values on a graph. It's crazy. The population of the US was roughly 1.23 times 10 to the 8th in 1930, and then 3.3 times 10 to the 8th in 2019. If the national debt were to be paid off by dividing the total amount evenly among all citizens, how much would each have owed in 1930? What about 2019? So 1930, we have to look at the debt, which was 1.6 times 10 to the 10 over the number of citizens, which is 1.3 times 10 to the 8th. And then 2019, we have the population is 22. So we're going to write this up. 2.2618 times 10 to the 13 divided. Oh, That is, yeah, that's our debt divided by the people, which is 3.3 times 10 to the 8th. So let's just go to Desmos and figure these out here. Okay. So in Desmos, I'm going to do 1.6 times 10 to the 10. And then on bottom, I have 1.23 times 10 to the 8. So to be paid off in 1930, every citizen would have owed $130.08. Let's see what it is now. And we could just copy this if we want. And Control C copies, and you can put it down here, and Control V paste, and then we can edit it. So this is 2.2618 times 10 to the 13. And then that is times 10 to the 8 still, but this is 3.3, I think. 3.3. And look at how much we all owe. Instead of $130, we all owe. Now, the cost of living is different too. So $1 in 1930 is not the same as $1 today. But that is crazy. We're each going to owe $68,000. That was 2019. Remember, now we owe 100 and some thousand. $68,539.39. Crazy. That is crazy. So I would like us to turn to the 1.6 applications on page 103, and we're gonna okay, we're gonna do a few of the problems here on page 103. According to statistics provided by the Internal Revenue Service in 2018, there were 154.4 million personal federal tax returns filed. That means 154.4 million people actually filed taxes. And the average amount of tax paid per filer was 10,903. Write each of these numbers in scientific notation. Okay, so filers would be 1.544 times 10 to the 6, I believe. Millions is to the 6. Let's go back to page here so I want to make sure. So millions is to the 6. So everybody sees that. Okay. And the other one is 10,000. So this is going to be 1.0903 times 10 to the 1, 2, 3, 4. Okay. Says how much money total did the government take in from these taxpayers? Perform the calculation, scientific notation, and write how you answered your answer to be pronounced. So that means we're going to do filers times money, because on average they each paid this amount of money. So 1.544 times 10 to the 6th star times 1.0903 times 10 to the 4th. And we're going to put this in Desmos here. Oh, 1.54 times 10 to the 6. And then we have 1.0903 times 10 to the 4. So it comes out to be 1.683423 times 10 to the 10. And times 10 to the 10, we said was billions, but let's just write this out. I'm going to share my paper with you. So there's our answer in scientific notation. And I'm going to move my decimal 10. 1, 2, 3, 4, 5, 6, 7, and 2 zeros, 8, 9, 10, 3 zeros. So 1, 6, 8, 3, 4, 2, 3, 2, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that is hundreds, thousands, millions. So 16 billion, so 16.8 billion dollars. And that's not even close because we said our budget earlier in a lesson was 2 trillion something. Wow. So this is talking about some money. Let's look at this one. The Earth is 9.3 times 10 to the 7th miles from the sun. What percentage of the way to the sun would that? Oh, we got back to the dollars, darn it. Let's look at it. An American dollar bill is 4.3 times 10 to the negative 3 inches thick. If all of the tax revenue from question 2 was paid in dollar bills, how many inches high would it be if they were all put in one stack? Okay, write your answer in decimal notation. So this many dollars, right? So 16.8. So we're going to do the 1.68342232 times 10 to the 10 times the thickness 4.3 times 10 to the negative 3. This is how thick it would be. And so I can just take this answer up here and multiply it again by the 4.3 times 10 to the negative 3. And my, it'd be 72387,197.6. And this would be inches. Wow. That's 72,000 inches thick. How many miles high is our stack of tax proceeds? So we have to take our 72,387, 197.6 inches and turn it into miles. How many miles high? So I can go from 12 inches to 1 foot. So I'm gonna go back and share my screen here. So actually, why don't we just take this instead of sharing our screen? Let's just leave it on the Desmos and let's just do it here. So we're going to take our 72,387, 197.6 inches and multiply that by 1 foot over 12 inches. So our inches cancel and we're in feet. And then we have to cancel out feet. So 1 mile over 5,280 feet. And that's if my, so yeah, 5,280. I want to make sure I had that right. So it looks like our stack is, I can just make this right here. So our stack is 1,142.5 miles high. That's crazy. Then question 5 says the Earth is 9.3 times 10 to the 7 miles from the sun. What percentage of the way to the sun would that big old stack of dollar bills reach? So what percentage? So these miles out of a percent, this miles, so 11,042.47 miles out of the distance to the sun. How far would that get us? Take us back to decimals here. So we are going to take 1142.47 and divide that by parentheses. I got to keep this together. 9.3 times 10 to the 7th. So that's 0.000123. We'll round that to. So there's 4 zeros. And that's actually in percent, that's actually 0.00123%. So just add a note here. And so that's actually 0.00. So eliminate 2 of those. So 0.00123% of the way to the sun. Wow. Okay. So I think you've got the hang of it. If you want to do more in 6, 7, and 8, you can send me some questions if you're that ambitious. Have a great day, and we'll see you soon.